In this lecture, which is going to be fairly short, we want to look at the definition of an exact equation. So there are some differential equations that are known as exact equations or exact differentials. And basically, when you have a differential equation that has some function of x and y times dx and another function of x and y times dy, and those are summed together equal to 0, then that's referred to as an exact equation. And so there are some solution techniques that we can use concerning exact equations. So first of all, what criteria do the differential equations have to satisfy in order to be defined as an exact equation? So here's our equation, and basically it's exact if it satisfies the following situations. So if the partial of m with respect to y is equal to the partial of n with respect to x, then we say that the differential equation is exact. So let's look at an example, because the easiest way to understand in this case is to look at an example. So here's an expression of a differential equation. So we have 2xy times dx plus x squared minus 1 times dy is equal to 0. And once again, we're still in first order differential equations here. So now we have from the previous page, so we'll go back to the previous page. Here's our definition of an exact differential equation. So we want to identify m and n. And then we want to force this condition to be true. And if it's true, then we have an exact equation. So m is equal to 2xy and n is equal to x squared minus 1. And so if we take the partial of m with respect to y and the partial of n with respect to x, we find that both of those are equal to 2x. So just to remind you what a partial derivative is, if you notice on m here we have 2xy, and we have two variables in this equation, x and y. And so a partial would be that we would take the derivative, a partial with respect to y would be we would take the derivative of this expression with respect to y only. So even though it's a function of x, too, we're going to treat x as a constant when we take a partial derivative. So when we take the partial derivative of this expression with respect to y, 2x just looks like a constant. In this case, we're taking the partial derivative of n with respect to x, and so this will differentiate into 2x, this will go to 0. So in this case, partial of m with respect to y is equal to partial of n with respect to x is equal to 2x. And so the equation is exact. Now, if an equation is exact, we say that there is some function of x and y such that the partial of f with respect to x is equal to m, and the partial of f with respect to y is equal to n. So if we now integrate, and let's integrate this side, the partial of f with respect to x, we get this function of x and y is x squared y plus some additional function that could be a function of y. Now let me explain this g of y. Remember that what we had was the partial of f with respect to x. So the original function f could have had all these terms in y only. And because it was a partial derivative, they're for all practical purposes going to look like constants. So when you integrate that, you get what you integrated from the function of x, and then you get all these other possible functions of y. So we have this g of y, and now we have to address that. So what we're going to do is we're going to take the partial of f with respect to y because we have an expression for that. So just to recap, we started with partial of f with respect to x. So we have two equations. And we started with the first equation and we integrated it to get this expression for f of x and y. Now we're going to utilize what we have here and what we know to be the partial of f with respect to y in order to figure out what this g of y is. So on the next page, the partial of f with respect to y from the previous page was known to be x squared minus 1. And then this expression, this x squared plus g prime of x, That is the derivative, the partial derivative of this expression here. So if we take the partial of f with respect to y, we'll get x squared, and then we'll get whatever the derivative of g with respect to y is. So that's where this expression comes in. Now, if we look at these two expressions, you can see that the x squareds will cancel out, and we'll have g prime of y is equal to minus 1, which means g of y is equal to minus y by integration. So now we take our f of x and y, which is x squared y minus y, and the solution of the equation is that this f of x and y is equal to some constant. And just like in previous examples, where if we had some initial conditions, we could evaluate the constant of integration, that's true here as well. If we have an initial condition on x and y, we can get a numerical value for c. So anyway, the reason to go over exact differential equations is they're not separable in the sense of the word that we talked about in the previous lecture, where we had a separable differential equation where we could separate the variables and integrate. But we do have these special techniques that can be used to solve exact differential equations.